Welcome. In this video, we'll learn how to use a multimeter to measure resistance, a fundamental step for working with resistive sensors and other electronic devices. We'll go through the process clearly and simply so you can apply it to your projects. This is the Ep.2 digital multimeter, a compact and portable device ideal for basic measurement tasks in electronics. Its design includes functions to measure AC/DC voltage, current, resistance, and continuity. It stands out for its ease of use, thanks to its intuitive rotary selector and clear display for easy reading of values. It's a versatile tool, perfect for beginners and maintenance tasks in basic electronic projects. The probes of the Ep.2 multimeter are designed to withstand up to 300 volts, ensuring safety and reliability for low and medium voltage measurements. The resistor code is a standard system used to identify the value and tolerance of electrical resistors using color bands. Each band represents a number, a multiplier, or a tolerance depending on its position. For example, a resistor with brown, black, and red bands has a value of 1 coulomb, 1000 ohms, while the fourth band, if present, indicates its tolerance, such as gold for 5%. This system is essential for quickly understanding resistor characteristics without the need for additional tools. Next, I will measure a 1 coulomb resistor connected in parallel. To do this, I will place the multimeter probes on both ends of the resistor, ensuring that the multimeter is set to the appropriate resistance range. This setup will provide an accurate reading of the resistive value without needing to disconnect the circuit, as long as no other components are connected that could affect the measurement. As you can see, I set it to a lower scale value using the selector, and this won't give me any measurement. You can do it in two ways. If you already know the resistor code, set the selector to the correct scale, or try each scale until you find the right one. Sometimes resistors get damaged and show values different from what the color code indicates, which is why it's always important to set the scale above the expected value. As you can see, it gives me a value very close to what the color code indicates. This is very common. Sometimes it's due to the precision of the multimeter or the quality of the resistor. This is indicated by the tolerance band. In this particular case, it's brown with a 1% tolerance, which is why the value is approximately 990 ohms. Now we will connect the resistors in series. They will share a single node. Nodes are common connection points for elements in a circuit. According to Ohm's law, the total value will be the sum of both resistors, so it should be close to 1980 ohms. Now we will place the resistors in parallel. This means they share the same pair of nodes. The result of this measurement should be calculated as 1 over the equivalent resistance is equal to the sum of the inverses of each resistor. For two equal resistors, the trick is that the resulting resistance is half the value of one resistor. For example, if I have two 1 coulomb resistors in parallel, the result should be half. which is 500 ohms minus the tolerance, approximately 495 ohms in our case. This trick is extremely useful when you don't have the exact values needed for circuit design or testing. Now we will look at potentiometers, and in this case, we're using a Trimpot. This component has 3 pins and is designed to precisely adjust resistance in electronic circuits. The number 202 marked on the top indicates its maximum value, which corresponds to 2 kiloohms, 20 followed by 2 zeros. Most potentiometers have this 3-pin configuration. The 2 outer pins represent the ends of the maximum resistance value, while the center pin, the wiper, allows you to vary the resistance between the outer pins depending on the adjustment. To measure it with a multimeter, place the probes on one outer pin and the center pin to get the variable resistance, or between the 2 outer pins to verify the potentiometer's maximum value. This design is common in Trimpots and other types of potentiometers due to its versatility in electronic applications. Now I will show an LDR, a component that changes its resistance based on the amount of light it receives. I tested it using the same methods as before, measuring with the multimeter. Initially, under ambient light, the resistance was approximately 2 coulombs. Then, when I covered the LDR to block the light, the resistance increased significantly to around 31 coulombs. This behavior is typical of LDRs and demonstrates how they can be used to detect changes in light in electronic applications. In conclusion, resistive sensors are essential components in electronics, and today we've explored how to measure and understand their functionality. Some common examples include the LDR for light, the potentiometer for manual adjustments, thermistors for temperature, flex sensors for motion detection, and resistive humidity sensors. Each has specific applications and plays a crucial role in innovative project designs. Thanks for watching. Please comment if there's something specific you'd like to learn. Remember to subscribe, activate the bell, and give us a like. See you next time.